Good evening, everybody. Welcome to another session of the workshop series, Shape Up the Future Professional, organized by the Electrical and Electronic Engineering Society of Faculty of Engineering, University of Peradeniya. Today's session is about the current trends in control and optimization of complex autonomous systems. From this session, you will be able to get an idea about what a CAS is and the optimization and control problems related to CAS, and also about the solutions that have been recently developed for those problems. The speaker for today is Dr. Shirantha Welikala, who is a proud graduate of our faculty, and he's also a Ph.D. and an MSc holder in systems engineering from the University of Boston. His main research interests are optimization and control of cooperative multi-agent systems, robotics, signal processing, and smart grid applications. Before starting, let me invite Mr. Praveen Rasanayaka, the President of Electrical and Electronic Engineering Society, to welcome you all. Over to you, Praveen.
Okay, thank you, Dilhara. So good evening, everyone. I would like to take this opportunity to welcome all who are joining with us today on behalf of Electrical and Electronic Engineering Society. First of all, I would like to warmly welcome the resource person of today's webinar, Dr. Shirantha Welikala, who is a graduate of our faculty, and as previously mentioned, he recently received his PhD in system engineering from the University of Boston, and he is one of the most suitable people to talk on this topic today. And next, I want to welcome Dr. Roshan Gurliadde, the advisor and the senior treasurer of EEES. And finally, I welcome all the participants who are joining with us today in this event. So this webinar is one of the EEES workshop and webinar series on Shape Up the Future Professional. We are intending to present you all with a career and research path that you can follow in the future. So today, Dr. Welikala will talk about complex autonomous systems and the current trends and in controlling and optimization of these systems, which is a trending topic in modern industry. So hope you will get the maximum out of today's webinar. Thank you all.
Thank you, Praveen. And now I would like to invite the senior treasurer and the advisor of EEES, Dr. Roshan Gurliadde, to speak a few words about the speaker today. Over to you, sir.
Okay, thank you. Yeah, actually, I think Dr. Shirantha Welikala, as mentioned by all of these people, is one of the best students that has been produced by this department. And first of all, I would like to thank him for agreeing to do this presentation, mainly due to the fact that we want our students to sort of get motivated and get the maximum out of their potential. And I think with Shirantha's long and successful, still budding research career, I think it will provide us with useful insights on not just what is relevant and what is trendy in controls, optimization, robotics and such, but his general experiences, how he has sort of planned towards this outcome. So all these things will hopefully be conveyed in this talk. And on top of that, I hope that the Q&A session will also be engaging, and I invite all the participants to actively participate and get whatever relevant information that you feel that you can get out of Dr. Shirantha. Right. So I'll conclude with that while thanking both the EEES committee as well as Dr. Welikala on this particular webinar. Thank you.
Thank you, sir. Without further ado, let's move on to today's session. Dear participants, as Dr. Roshan Gurliadde mentioned, we have a very valuable resource person today. So we hope you will get the best out of today's session. Now, I cordially invite Dr. Shirantha Welikala to start the session.
Hello, everybody. I hope everyone can hear me. Right.
Yes, it's clear.
Okay, right. Thank you very much for the introduction, Dr. Roshan Gurliadde, and thank you very much for the invitation for me, and I will write my presentation straight away. So today's presentation is about current trends in control and optimization of complex autonomous systems. So I decided to talk about this is because this is somewhat related to my current my PhD as well as some of the stuff that I did in my undergraduate years at Peradere. First of all, let's look at what is these three parts of the title means. So a complex autonomous system, from my definition, is a collection of agents where each agent can control its state and aims to collectively optimize some global objective. So why I call this a complex system? It is because mainly the agents and the environment that we consider can have complex dynamics. And I call this autonomous because each agent is assumed to have its control over its local state. And so this is one example of such a complex autonomous system where a fleet of where we are interested in placing a fleet of vision sensors in a residential place. And another example is one where we deploy a fleet of mobile robots in order to persistently monitor a given set of points that are interest to us. So these are some of the complex autonomous systems that constantly arise in different applications. So then let's see what's optimization, what's control, and what is the difference there. So the optimization is about obtaining a fixed set of global states, and the control is about obtaining a globally optimal set of controls. That means a state trajectory. So the difference is here it's like solving an equation, and here it's like solving a differential equation. What we get is a trajectory, whereas in the optimization case we get a fixed set of variable values. So again, a coverage. The first example that I showed is an optimization problem, because we only need to know what is the place that we need to place our sensors. So this is also known as this particular example is known as coverage problems. And the second one, where we are interested in about agent trajectories, obtaining optimal agent trajectories, it's a control problem, and this particular example is known as persistent monitoring problems. So this is my outline of today's presentation, and as you can see, I will talk about the coverage problems and the persistent monitoring problems. And after introducing each of these problems, I will talk about the high-level approach to those problems, as well as low-level concerns and solutions that we have developed to handle these problems. So under each of these sections, I will introduce concepts like boosting functions, control barrier functions, wind-driven receding horizon control, and classical optimal control. And these are what I mean by current trends in my title. So yeah, let's first let's look at one of the motivations that that not only motivated my PhD study, but also some of the stuff that I did in my undergraduate years. So let me see whether I can play this video. Can you see my screen? Yeah, it looks like I have to do it this way. Okay, so this is a scenario from a movie called Prometheus, where let's see what happens. It's about deploying a team of agents, these robots, to create a map of an environment. So this was, I saw this movie when I started my undergraduate studies, and I was interested about developing such a robot. And in my final year project, I worked on a robot where we only focused on a robot, developing a robot control system and its navigation, vision system development, and the embedded system development. Those kind of low-level problems arise in developing such robots. So we studied that in the undergraduate years, and in the in graduate studies, I was lucky enough to study. Let's see. I was able to go to the more high-level view of this problem, whereas how to design teams of agents and how to make them achieve the certain objectives, sensing and monitoring type of objectives. And yeah, so that's the motivation that I had. And let's move on to the first part, about the coverage problem. So the coverage problem is about the goal is, given a mission space, we need to place a fleet of N agents in an optimal configuration. See, optimality in the sense of optimizing some objective function given. So this is one example. This is a square-shaped mission space with you can see 4 agents I have been placed, and the yellow-colored regions are what we call lightly covered regions, and the green-colored regions are highly covered regions. So we need to place the agents so that we completely cover the area. So this is the objective function, and typical coverage objective function takes this kind of a form, where R is the value of a point and P is, can we think of some interaction between the agent configuration and different locations. So this is a surface integral over the mission space. So you don't need to go into too much of the details. I just wanted to show you an example of a coverage objective, how it looks like, so you can get some idea about what I'm talking. So these kind of problems arise in multitude of applications. For example, in surveillance, like I mentioned, when we need to monitor a certain building, and we need to, say, place vision sensors. So these agents can be vision sensors, as well as you can think of it as a set of Wi-Fi routers or lights or temperature sensors or whatever. So that's that. And even this occurs in large scale applications, like in wireless networks, when you want to place set of signal towers so that it covers consumers in a certain area. And urban planning, that is also another application, which is even large scale application. In robotics, if you want to place set of robots uniformly over some area, then we can use this coverage problem to find the robot locations. So another application is if you want to discretize some area uniformly, then we can think of each of these discretized points as robots, agents, and we can simply run a coverage problem and find out what are the optimum locations so that they optimally cover a certain area. So those are the applications. So as I mentioned before, I take 2-level approach to solve this problem. The first I call the high-level problem is the problem of finding the optimum configuration. And the second one is often after we finding the optimum locations, we need to deploy mobile agents to those locations. So this, while the high-level problem is sufficient for most of the applications, there are applications where we need to deploy robots and where the procedure that an agent needs to take in order to converge to their optimum positions is also important. So first I'll talk about the high level, and then I will move talk about the low level approach where, yeah, let's get into the first part. So as I said, this is a typical coverage objective, and the problem is to solve this optimization problem. So I'm not sure about how much familiar you are with the optimization problems, but I remember in third year there was a optimization elective So I think you should be able to familiar with this notation. So this simply means we are interested in finding the argument, which is S, that maximizes this function value. So the only reason that we cannot solve this problem straight away, for example, in your advanced level knowledge, when we have to maximize some function, all we have to do is take the derivative and equate it to 0 and solve for the variable. So what that makes this difficult to do is these objective function and the feasible space are very complex. And therefore it's difficult to solve it like that. For example, if I take the gradient, it would look like this. So which is very difficult to equate to 0 and get the argument, that the optimum argument. So these kind of optimization problems are not straightforward, but there are techniques that can be used to solve these problems, like particle swarm optimization, generic algorithm, and ant colony optimization. So, but the thing is, these methods, even though they are widely researched, they in practical scenarios, it's difficult to use them because they are computationally expensive and have a slow convergence rates, and they have the introduced randomness component in it. So all these things make it difficult to use such algorithms. And here we take a different, slightly simplified approach, which is just to follow the gradient. So this is called the gradient descent. So the gradient descent is also, I think, in third year course, I think you should be able to familiar with this one. And so the basic idea is just keep on updating our variables following the gradient. So, and this process will end when the gradient is 0, which is the point that we need to find, right? So in coverage problems, often we do not need to update all the variables at once. We can allow each agent to update their own variables. So this is called the distributed gradient ascent. So this is what we are using. And the obvious advantages are that they are computationally efficient, fast, and easy to analyze, because they doesn't have any randomness component to it. They are easy to analyze and study the performance of systems. So the only disadvantage of this gradient ascent approach is that it will converge to the nearest or a local optimum, an optimum point, which can be a local optimum, and depending on the initial location that we started. So that's an issue that arises in whenever we use gradient ascent. So to address this, what we have introduced in our research is called a boosting functions approach. So the motivation here is that we first use the gradient ascent, and as soon as it stops, that means when the gradient becomes 0, we switch the objective function that we use, and we switch to what we call a boosting function, and then ask the agent to follow that direction. And once that also stops, we again switch to the original objective function and ask the agent to follow that again, and then see where we end up. So in this example, you can see that this boosting function was helpful for the agent to escape from this local optimum point and eventually converge to this global objective function. So the global optimum point. And so this is because of the boosting function that we use. So here, in this paper, we have provided one application and several ways of designing these kind of boosting functions, so that people can use gradient ascent and still get to a good optimum solutions. So these are some of the advantages that we have using this strategy. So it forces the agents to escape local optimum points, and it can be seen as a controlled form of randomizing the solution, and it make use of the properties of the objective function that we study. So we have also proposed what we call a distributed boosting scheme, which details how each agent should use its normal modes where it follows the local objective function, and the boosting modes where it follows the boosted gradient direction. So and we have come up with theorems about the how to guarantee the convergence of these kind of distributed boosting processes, but those details are not that important for today's presentation. I will show you directly some of the results that we got with and without boosting. Okay, so in the left-hand side, it's without boosting. That means simply using gradient as n. And in the right-hand side, it's with boosting. You can see that the agent was able to escape this position and come to a better position where it can cover a lot of ground. Another similar example with multiple agents is like this. So it's again shows a good performance improvement. And these are some of the other similar experimental results with boosting and without boosting. So you can see that it's not trivial how the end result is, but it's obviously achieves a better performance improvement. Right. So with that, I'll move on to the low-level problem of the coverage problem. And so the low-level problem is, as I mentioned before, it's about moving the agents to the optimum points that we found. So what are the challenges in this scenario? The first challenge is we need to first solve an assignment problem which tells that which agent should go to which of the solution points that we found. So this is kind of straightforward. It's if you took the third year OR operations research course, it will discuss several techniques to solve these kind of assignment problems, and it's not a hard problem to solve. So I will skip that step and talk about the convergence, how to guarantee the convergence of the robots to the optimum points. And then I'll talk about how to guarantee the safety. So in safety, what I mean is that each agent should avoid hitting obstacles, right? So one easy way to do that is shown here. So this is called the waypoint tracking scenario, where we have put waypoints around the obstacles, and they use them to find the optimum trajectories. But this is a simple way, but in the presentation, I'll detail more complex approach. And we also need to avoid hitting other agents, because we are obviously dealing with multiple agents, and there can be other constraints as well. So all these three are considered as safety concerns. And while we do that, we also need to optimize the energy consumption associated with the agents. So I'll next detail you how we can overcome these challenges. So first, let's look at the convergence, how to guarantee the convergence. So for this, we use Lyapunov control. I'm pretty sure if you haven't taken the finally a nonlinear control module in Peradeniya, you haven't heard about this, but I will be presenting the basic concept here. You don't have to worry about it. So here we consider an agent dynamic model, which is this kind of agent dynamic model, which is called affine nonlinear model. So this is kind of similar to the usual linear system model, x dot equal ax times bu. The only thing is ax is replaced by f and b is replaced by g. So one example system that takes this particular form is the second order unicycle model. So this is a robot model that often used in literature to validate certain control algorithms. So that's that. And so in this kind of system, if what we are interested in is making the state goes to zero by convergence. So this may correspond to making the robot's location to the optimum location that we found in the coverage application. So I will be talking about this, but it really means this constraint. So in Lyapunov control is based on what we call a Lyapunov function. This you can think of it as simply the energy of the system that you consider. So you can always write an energy equation for the energy. So that means you can at least now you can assume that you can write a Lyapunov function. So that's something you have. And if you consider the time derivative of this one, and note that it will be a function of both x and u, because when you take the derivative, you have to multiply it by, first you have to take the derivative with respect to x, and then you have to take the derivative of x with respect to time, which is this. So that means u will show up in this expression. So that's why I write this as both function of x and u. So the idea of Lyapunov control is to find a feedback control law that takes this form, u equal kx, k, this is a function of x, which will result this inequality. So here, this is in linear systems, I'm pretty sure you are familiar with the control law u is equal to k times x. So this is that in nonlinear controls, it's basically a function of x. So if we can find a control law that satisfies this inequality, then it guarantees the achieving of this constraint, which is called the stabilization of the system. So that's the way that we are going to achieve the convergence. And the main concern here is that deriving controls like this form is not straightforward, especially when the system is complex. So instead, what we try to do is we try to construct a set of these controls and which will still guarantee the stabilization of the system. So the control Lyapunov functions and provides this kind of a set. Here I have written it here. So if our Lyapunov function satisfies this condition, we can then find a set of controls, not only one control, but a set of controls that will make sure the system will stabilize. So this will come in handy later on. So let's just move on to the next part, which is about guaranteeing the safety. So all the safety concerns, we can write it in this kind of, as a set. So this means in the state space, we know a certain safe set where the agent can stay there and it will be safe. And this boundary is what we call the barrier function. And so in order to guarantee the safety, but in the literature, it says that we need to prove that this safe set should be forward invariant. That means if we start the agent in a safe set, we should prove that this safe set is forward invariant. So if that is the case, then we call the system is safe. So then in order to guarantee this forward invariance, control barrier functions provide an approach where again we construct a set of controls that will guarantee these safety concerns. So that means if we select a control from this particular set, then it will guarantee that our system, that is the agent, will stay safe. Right. So the basic idea here is, the summary is this one. We don't derive a closed form equation, but we try to derive a control from these two sets because one guarantees the convergence and the other one guarantees the safety. So next, the last concern is optimizing the energy. So this is one candidate one can think of for the energy. This is U transpose U, which is basically the U squared. So in order to maximize this kind of energy, minimize this kind of an energy, what we do is we first discretize the time and assume that within a certain discretized interval, assume the state is constant, and solve this kind of an what we call a quadratic program in order to find the best controller that will minimize the energy as well as guarantees the asymptotic convergence and the safety. So this will give you a controller that will address all these three concerns: the safety, convergence, and the energy optimization. So that's what we call the control barrier function approach, right? So once we get this U, we apply that and then update the state. That means the robot will move to the next position, and then we again do the same. We again solve another quadratic program, which is simply an optimization problem again, and then apply that control. So the process will continue like that. So that's how we do that. So this is an example video to illustrate this concept of boosting the barrier functions. So these blue colored areas are, you can think of them as other agents, and this agent is trying to go to a destination while other agents are also moving in the environment. And yeah, as you can see in this video, now he was able to avoid a lot of the all the obstacles and move to the destination point, and we can change the destination point and ask the agent to go again. And yeah, let's see what happens. Yeah, you can see moving obstacles again. And so that's the basic idea. So it will allow the agent to move without hitting other agents while also optimizing energy to reach different destinations in the mission space. Right. So with that, I think I'll move to the second part, which is about the persistent monitoring problems. The persistent monitoring problems is different from coverage problems, which is that is because now we are interested not only about finding a set of destination optimum points, but we are trying to find optimum agent trajectories. So like coverage problems, persistent monitoring problems have a large number of applications. So we call a persistent monitoring problem arises whenever a dynamically changing environment needs to be monitored by a set of mobile agents. So so the main components in this kind of a persistent monitoring problem setup obviously we have set of agents, set of targets. Here I have marked them in stars. So those targets are the points of interest that we have, and the points that the agent needs to sense. And we assume that there are certain trajectory segments already laid out for us, so that the agent only have to travel on those trajectory segments. So so this kind of a problem setup, we can abstract it by a network, simple network. So we don't need to, every time we don't need to think about these curves. So we can see it as a system where we have set of targets and set of edges and like that. So it's much simple to deal with, especially when we are handling this problem at a higher level, when we try to find the agent trajectories. So in terms of the applications, so these kind of systems arise in data collecting, surveillance, sensing applications. For example, these target points, you can think of it as sensors that collects data regularly, and the agent, you can think of it as some data collecting robot. So he visits the sensors and try to collect the accumulated data, right? So this persistent monitoring problems arise in different application domains like transportation, smart grids, smart cities, and manufacturing. For example, one application in transportation is that, for example, you can see this as a bus traveling in a certain route where there are passengers building up, and the bus needs to optimize its trajectory, and so that the waiting passengers are, the overall number of waiting passengers are minimized. So like that, I can provide examples of how this resembles certain problems arise in manufacturing as well, but let's go into the details. So again, here also I use a bi-level approach, where in high level, I assume that each of the trajectory segments have a certain travel time value associated with it that will take the agent to travel on that edge. So this assumption allows us to only think about solving the optimal sequence of target visits for each agent, and the corresponding dwell times to be spent at each agent collecting information from these points of interest. So that's the high level approach, the high level problem. So it only try to find these optimal sequences. In contrast, the lower level problem tries to find the agent controllers so that it can drive the agent smoothly in these kind of trajectories. So it will no longer use the previous assumption that there is a fixed time value that is given to us, which will take the agent to travel between the targets. But it will consider the agent dynamics as well as agent energy in generating the in solving the problem. So first, let's look at the high level problem. And the state, in order to describe this, the environment that we are considering, a persistent monitoring environment, we define the state. So the state of this kind of a system is defined as the target states and the agent states. So agent states are in this high level, only agent state is basically the location of the agent. So it's not that important to us. What will play a major role is the target states. So the target states are assumed as some uncertainty level that needs to be sensed by the visiting agents. So each, as I have shown in this video, each uncertainty state, which is drawn in yellow color, has certain dynamics to it. And we need to control them by the agent, by controlling the agent. So that's the target, that's the objective here. So this is the target dynamic model that we are using. There are different dynamic models, but this is a common dynamic model used in these kind of persistent monitoring problems, because this is intuitive, because it is like this. This simply means target uncertainty will increase whenever there is no agent visiting the target. But as soon as an agent visits this target, its uncertainty state, Ri, will start decreasing, and the rate of decrease will be proportional to the number of agents residing in the target, and it will never go below 0. So that's the basic way that this target uncertainty behaves. And so that's the target dynamics. The agent dynamics are, as I said before, in the high level, we do not really care about the agent dynamics, because we assume that there is a fixed travel time value that the agent have to spend whenever he needs to travel between the targets. Yeah, so that's that. And the main objective of this persistent monitoring task is to maintain these target uncertainty values, this average value computed over the target uncertainty values minimized. So this is basically a finite horizon average of target states. So the solution that we seek here is, as I said, it's each agent's optimal sequences of targets to visits and the dwell times to be spent. So finding these kind of optimal sequences is in a given network is a very difficult problem. For example, I think you might have already heard about the traveling salesman problem, which is about there are a set of cities interconnected to each other, and we need to find the optimal sequence of cities that a salesman need to travel so that he can cover all the cities. So for that problem, even though sounds simple, it's a very hard problem in the optimization and operations research community. That's kind of a baseline. If something is harder than that, it's definitely a hard problem to solve. So this persistent monitoring problem is way complicated than that. So so what we propose here is we try to break this problem down to different parts, so that we can get a handle of this complexity. So what we do is we break the problem down so that to set of subproblems where the agents can independently solve those small subproblems, and while they are executing their trajectories. So just to give an idea, if we consider a scenario where an agent is at certain target I at some event time t, so the immediate control decisions that it has to take are these three. It has to decide how long it will have to stay in this current target, and what target is to be visited next, and the dwell time to be spent at the next target. So these are the control decisions an agent face at some time t. So we can write these the control variable combining those through those control decisions. And in order to find the optimal set of controls, we only use we constrain the agent to only use locally available information. So that's because we need to make our solution a distributed solution where agents do not need global information. So and let's say we have a planning horizon given by a user, then receding horizon control solutions. I'm not sure whether you have heard this type of controls. So the idea behind receding horizon control is to solve this kind of an optimization problem to find the optimal controls. So this optimization problem objective function involves basically simply two components. One is the immediate cost over the planning horizon, and the other term is the future cost beyond the planning horizon, depending on the state at the end of the planning horizon. So receding horizon control is basically that. So these kind of controls have been developed not only for these kind of complex systems, but also for very simple linear systems as well. So I will be using this kind of receding horizon controller because it's really convenient, and it can be executed in a distributed manner without using the global information. So and in this receding horizon control approach, we call it an event driven, because this receding horizon controller will be evaluated only upon events that agents observed. So once we find these optimal controls, then the agent will execute these controls until it observes another, the subsequent event in its trajectory. So only then it will reevaluate this problem and find what will be his next set of controls. So that's how this event-driven receding horizon controller works. So we use this form, but we do a number of modifications so that we have certain set of qualities in our solution. So I won't go into details of these qualities, but one of them is like we remove this future cost term just to simplify the problem. And then we, as the immediate cost term, we use a simplified version of the global objective. So as you can remember, this is the global objective function that I showed, where the team of agents are interested in optimizing this one. But the locally, what the agent can get about this is this kind of a function value. So, and the next modification is we get rid of this h, which is a parameter that is given to us by a user. We get rid of that by introducing something called a variable horizon. You don't need to get into details, but the bottom line is we not only just take the standard controller, we always have to do a set of modifications so that it matches our needs. So after doing those modifications, we end up like problem like this. And again, there are a few another set of modifications to do, but I'll not go into details. And those modifications will further not simplify, but implementation-wise simplify the problem. So this problem is difficult to solve because it has continuous variables as well as discrete variables in it. So what this modification does is it just divides it into two stages where continuous control decisions are solved in one problem and the discrete control decision is solved in the second problem. So this will give us the optimal control decisions as well as the optimal planning horizon. Yeah, so for this particular persistent monitoring problem, it turns out there are three kind of receding horizon control problems that will arise depending on the event that triggered the persistent monitoring problem. So this turns out to be even though there are three kinds of problems, after studying each of these problems, it turns out all of these problems can be solved if I added this solution to this particular problem. So then what we did was we were able to just using the simple geometry. So this, and we were able to get a closed form solution to this optimization problem. So once we have a closed form solution, that means we can solve any of these kind of problems that the agents will face in their trajectories. And that will allow each agent to find their optimal controls without any processing delay, because we have closed form solution to all the problems that can arise. So about this optimization problem, it's pretty, even though it looks complicated, it's pretty simple one, because this part you can see it as the rational function that we call in advanced level. So this is simply a set of constraints that will limit the control variables to this kind of an area. So all we have to do is find an equation for the best value within this area for this this function. So it was pretty, even though not straightforward, it's an easy problem to solve. And it really needed only the advanced level knowledge. So yeah, so this is one example where I have applied the set controller for configuration with 3 agents and 10 targets. So you can see that agents will move, and keep in mind that they only have local information. That means they will only know what is happening nearby, in the nearby targets. They won't know what is happening at the end of these network. But still, they have been they can manage to observe all the targets equally and in a uniform manner. And then what we did was, as usual, we compared it to one of the existing solutions, and it turns out the performance improvement is huge. It's across several examples shown here. It's around performance improves by 66%, and so that's pretty huge. And the other thing is, compared to this method, this receding horizon control method have set of structural advantages to it, like it's parameter free, gradient free, initialization free, and those kind of these are really the benefits that we seek in a real world applications. So these are pretty useful when we are going to apply to this in a real world scenarios. Okay. So with that, I will go into the provide you with the details of how this persistent monitoring problem is solved, but considering some of the low-level concerns. So here the goal is to drive the agents in optimal trajectories. So the challenges are, first, we have to control the agents in these trajectory segments, and we have to again consider some constraints to the state and the control, and also we need to optimize the energy of the agents. Okay, so here again we use the Unicycle model. As I said, this is some model. This model is widely used in a control community to verify algorithms. Regarding the energy objective, as I said before, now we have to optimize the energy. So what we do is, previously we had this part, we only had this part. Now, since we need to optimize the energy, we also add that to the objective function. And because of the energy concern and the agent dynamics, no longer we are assuming that there is a fixed travel time that the agent will take. From now on, we will assume that the travel time will be determined by the optimal controls that we find for the agent. So one thing we can use to simplify this dynamic model is the fact that the shape of the trajectory segment is fixed. So if we use that, we can simply use the kinematics of the robots to simplify this unicycle model into a simple linear control model, linear control system, right? So this is this kind of systems, I think I'm pretty sure you have seen them. And these kind of systems, there are standard control solutions. So that's why we use this kinematics and get this one. So now again, we have to look at what's the control decisions that the agent have to take in this kind of scenario. So still he will have to make the dwell time decisions, but now on top of that, it'll have to decide what will be its acceleration, the tangential acceleration, and as a result, it will get the travel time values. So the optimal control decisions, which is basically these dwell time values and the tangential acceleration profile, will be given by this kind of a optimization problem. So this is, if you remember the global objective function that I just showed before, this is basically, I'm trying to write a simplified version for each of the agent to use. So this is the energy component and the monitoring component of the receding horizon control problem that the agents solve. So previously we only had, as you might remember, we only had this in the receding horizon control problem, but now we have the energy component. So that's the only difference. And now we can convert this problem. It turns out to be a simple standard optimal control problem. So this problem is one that has been studied in the literature in 1960s. So there is a textbook solution to this one. So that's we just have to use that and find out what is the optimal travel time and the acceleration profile. So even though this looks kind of messy, it simply says just use an acceleration profile that is continuously decreasing, and that means if we have the optimal controller, the velocity profile would be something like this, quadratic form. So now again, as I did before, we just compare the performance with and without the optimal control solution that I just saw. And it turns out in the the global objective function, which is the sum of the energy objective and the sensing, the monitoring objective, it basically halves the cost value. And here you can see that when we use the optimal controller, it will the monitoring cost is worse than before, but the energy wise, it saves a lot, so that it eventually the global objective function wise, it saves it provides a significant improvement. Right. So this is again another video. Let's see. Yeah. So now compared to before, you might able to see that sometimes agents move really fast to the destination targets. Sometimes they intentionally slow down in order to save the energy. But they managed to cover all the targets, and yeah, the main difference compared to the previous video is that their speed is varying now. Right. So to summarize everything that I did, yeah. So these are the 4 parts. The first, we talked about the boosting functions approach, which is basically an optimization technique where we change the objective function intermittently so that our solution converges to a better solution. So that's the boosting function idea. And then I talked about the control barrier functions, which allows us to control agents while guaranteeing some safety as well as convergence, and also minimizing energy. So this is kind of an optimal control solution, but with some added benefits. So next I talked about event-driven receding horizon control. So it basically is a function, it's an optimization problem that is solved at different points of time, considering immediate cost and a future cost. And we saw how it is used for the persistent monitoring problems. And finally, I came back to using a very conventional tool, which is classical optimal control. So this is because even how complicated systems are these days, when you do some modifications and treat the system in different ways, you can still end up with classical problems where there are standard textbook solutions. So that's why classical optimal control is even used in even today. It's been researched while there are very new concepts like boosting functions, control barrier functions. All right. So regarding the control barrier function, this is really a hot topic these days, because it really allows the controllers to guarantee the safety, which is not something available in classical optimal control. So yeah, that's that. And I want to thank my advisor, because most of the work I showed, it's from papers that we published with my advisor. And I want to thank my colleague, Wei Xiao. He's the actually expert in the control barrier functions, and we hope to publish something combining control barrier functions with coverage problems. But he helped me with he's the one that provided the video that showed the control barrier functions. So I must thank him, and I really need to thank Dr. Goldeb, because he's the one organized invited me initially to this talk, and I think it's very nice opportunity for me, because I came from Peradeniya, and this is my first talk or a webinar like this after getting the PhD. So I think it's a really good opportunity, and so I make it. I want to thank some of the faculty members in University of Peradeniya, with whom I got the opportunity to do research. Dr. Parakram Eknayaka, Professor J.B. Eknayaka, Professor Janaka Vijayakula, and Dr. Lilan Sabaranayaka, and all the faculty members that I got to learn from. I also want to thank the organizing committee and the Mr. Sanlu for managing the talk. Right. Now I am open to answer any questions that you have, not only about this research and the specific topic that I discussed, about the higher studies in general. If you have any concerns, I like to answer them now.
So I think you all can, as Welikala told you all, you can focus your questions on like the talk that he presented, and also about general avenues of research as well. So in Welikala's case, maybe you can also mention a little bit about like your future direction as well. Like, for example, what are you going to do post PhD? And for example, for someone like you who has done research in this particular manner, like what are the opportunities that are present as well? Shirantha, can you give a little bit of insight on
sure.
that as well?
Yeah, so, sure. So my immediate future plans is I'm joining University of Notre Dame in Indiana, USA, as a postdoc. So where I will continue this same research about autonomous systems, multi-agent system, what we call is multi-agent systems control. And I'm hoping to for the focus on these persistent monitoring problems and coverage problems, because it seems to me that I always have been interested in these problems from the get-go. So
do you see an analogy like between what you did way back in the undergraduate? Like, for example, I think something that we did not mention is that you did multiple projects, right? Like, for example, like from the third year to the final year, you worked on something more related to robotics, autonomous navigation, that kind of work. Then you where I think Lilantha, Dr. Janaka, myself, and Parakrama were involved with you. But then after graduation, you went on to the smart grid research, where you again worked with me, Parakrama, and Professor Janaka, right? But in that initial one, in the final year projects, even though this is not, like in a depth sense similar, but there is that sort of inclination, right? So there is that leaning towards that area in your work. But also I want to ask something technical with regard to the barrier functions and all of that. So this is something that is motivated by a certain classical branch of control. So like what has been the motivations there? I noticed about like forward invariant sets and things like that being mentioned, and also where you talked about like a class of control. So I was just wondering, like when you said that, do you actually go for like a fixed set of control solutions? Or like, is it really optimal at that sense? Or is it like you just have a reservoir and below that you can pick and choose any one of those controls that satisfies that sort of barrier, or that, like what you call that, the safety region or whatever?
Yeah. So this is optimal. This is a optimal solution. So
it's completely globally optimal is what you're saying, right?
Yes, because here the thing is, as you can see here, even the objective function is pretty quadratic, and these constraints, even though I haven't mentioned the specific form, these are linear. Turns out to be linear
I see.
Functions of U. So this is pretty easy one to solve. So the only concern is here that we have to discretize and solve it at every time instant.
Okay. So repetition is what you are saying, no?
Yes. So it's not like classical controls where we derive a closed form equation and that will work for every control.
So because I was just thinking, I was just thinking like you have this, it's easier for me to describe with the video. Like I was just thinking that you had this sort of like, rather than going into the minima, you actually had an entire pool to work with. So you pick and choose something in that reservoir or something like that. That's not what you meant, right? Not like that. Just a very specific minimum location is what you were talking about there, no?
Yes. Yes, but that is found through this one. But it is true that there is a reservoir of control values that we can choose. But these are control values for a certain state. So it's true that there is a reservoir, but within that reservoir, we select the optimal value to select, which will satisfy both of these concerns. So it was motivated by the classical, as you said, it's classical
that's the other question I had, like, was it more, I mean, what were the leanings and you know, like whether, because I'm pretty sure like most of the things that we do encounter, I mean, what happens is, you see, I mean, interestingly, at the very end, you came full circle and went back into something which was very classical optimal, you know, control as well, right? So you suggested there as well, that particular point. And one other thing was like with regard to the boosting function. So you do this completely to boost towards a global optima, or do you like use it like sometimes when you have like a trajectory that is stuck somewhere in the valley? Like sometimes I remember like when we used to optimize like you know, complex valued surfaces, sometimes when you have a what do you call that, a sort of solution sort of stuck in some sort of a cavity, you know, if you want to
inflection points, this kind of stuff, right? Yes, so exactly. Yes, this can be used at those kind of situations as well, because this is basically the simple idea is you just forget about the objective function that you were using and just start thinking about a new objective function. And that can be used whenever if you are not satisfied with the solution that you use, you can use that. But the catch here is that in order to define these functions, you have to have some sense of which solutions might be better. So in order to design these what I call boosting functions, we have to have some idea where the system should move, where there might be better solutions. For example,
so I mean, you use the word randomized. So as you said, it's control randomized, right? That's what you that's what you are doing, right?
Yes, exactly. So we are not trying to randomly move the solution. Here we are trying to push the solution towards a certain direction where we think there might be a solution in that direction. So that's why that's what I meant by we are doing randomization, but in a more smart, systematic way.
So it's actually one of those sort of tools that is like global, right? It's not something that is just applicable to, you know, controls, robotics domain. It's something that is very, very overreaching, correct?
Yes. As you have seen here, the control and optimization, they both go hand in hand, because for example, here I started with a control problem and eventually end up in an optimization problem, because this is simply an optimization problem. So it's they overlap, and whatever the problem is, you can use these techniques. Yes.
And now something a little bit more broad. I'm sure the others will have some questions as well. Now, in your case, like, let's say in your case, I'm assuming you are following down the research track. Like there are a lot of third years, second years, you know, final years as well in this particular audience. So in your case, like, would you say like in your group, what are the options that you saw? Like, for example, did you see a lot of students going towards the academia, or did these people go into the US industry, or did they go into you know, other countries? And generally, for example, generally, like from your experience, like for controls and robotics these days, simply put, around Boston, you know, what are the key sort of hot topics? Give us a little bit of insight on those things as well.
Yes, exactly. That's really great question. So in my batch, we had around 13 students. I'm the second one to graduate, so I don't know where the others will go. But from my I know the seniors. So most of them go to the industry. Only few go to the academia, because the industry is very lucrative, you know. And there are a lot of companies around Boston, and so people like to put
examples, like just give them a little bit of feeling.
So for example, from my lab, I know people went to Facebook. They manage with how to optimize the advertisements and those kind of stuff, which is completely about nothing about the controls, but completely about optimization. And there are people who went to areas like Uber, those kind of applications where transportation is involved. And there are people who went to the other, of course, the academia, but I know very few people.
So I think it's an interesting point, right? Because I remember, like, when I was talking with some other people who did signal processing research, you know, we see people not just going for standard electrical engineering, we see people going for like investment bank. So here you are bringing up another point exactly similar, right? Like, for example, with guys who are going for control and optimization, we see people going into very non-electrical and compute engineering fields as well as opportunities. No,
exactly. So one important thing, we recently had a graduate student in my senior year. She joined government policy planning job. It's about air traffic control and developing policies for that. I don't know beyond that, but it's, I know that it's.
We get the idea, right? Because at the end of the day, it's more about like looking at it in a very applied mathematics sense and not limiting towards engineering, but towards all types of applications. And in this particular case, I think it has more to do with the fact that maybe, like, even though you get a degree in engineering, you don't limit yourself to just engineering jobs, right? That's the bottom line.
Yeah, exactly. So it's about using maths. So systems in engineering is, I often consider that just applied mathematics.
Exactly.
It's not that into engineering, because we don't deal with the very low level issues that come when we have to use hardware. For example, in my PhD, I always use simulators, and there are students who deal with the hardware, but the thing is, we don't spend too much time on the issues, solving hardware related issues. We look at the upper level, we look at the math, and we look at the proofs, we look at those kind of concerns more. So which is good, which was good for me, because the fact that I didn't have to work on hardware during the pandemic last year, I was pretty glad about it.
And how, I mean, I'm trying to remember, like, what was the duration for your PhD? How long did it take for you to complete it, Welikala?
It's 3.5 years.
3.5 years, right? So, for example, for those who are wondering, like a US PhD also with proper sort of maturity, you can actually get it done within 3.5 years, right? So this is
Yes, but I must say it'll be 3.5 is you'll have to.
Yeah, it's an exception to the rule, by the way, right? Because I think we'll also have to make. I mean, like, for example, I would assume that already you would have had multiple publications, and what happened there? Like, in terms of publications, maybe you can give some insight to some of the people who want to go for PhDs as well. Like, how many publications you covered during your PhD? Like, what happened there?
Oh, in the PhD. So I have.
And even before that, also you can mention, because maybe some of these people don't know your entire credentials.
I think I have significant number of publications when I came in. So I was pretty comfortable with writing papers, and I knew how to manage multiple research projects, so that eventually I come up with something publishable. So that's a very good skill I think I picked up from basically working under you. So in Peradini, in different projects. So I think that's really helpful. So when to answer your question, I had I think 3 very high quality journal papers when I came in, when I started PhD, and more than 5 IEEE conference papers. That's before I start PhD. So right now I think I have 4 journal papers in places like
4 new journal papers, right? That is in
Yes,
addition to the earlier
yes,
4 journals, right? That's what you're saying.
yes, and currently working on 2 more papers, and I'm hoping to submit them before I go to the next placement. So it'll be add up to something more than 6 papers, journal papers with all of them I being the first author, and the second author is professor. Yeah.
And I think in your case, you already like, even before the PhD, you had like multiple presidential awards from the publications you had with myself, Parakram, and Professor Janaka. And now you have another bunch, and I think probably your H index itself is now in double digits, if I remember correctly, right? At least it's close to that, right?
No, it's still. I think still my recent publications needs to.
They need to be
needs more time. Needs more time. Yeah. But it'll go to, sure, it'll go to
so now
double
like,
digits.
I'm just wondering, like maybe some of the others may, Praveen, is there anybody who wishes to clarify? Because that's why I went from the technical to the general, because people might have different questions on different avenues. So maybe some of them can, what is the mechanism that you use, Praveen? Do you ask them to like give them a written sort of form, or do you allow them to raise their hands and ask the question from the presenter?
It's okay both the ways.
Yeah, so if anybody's, and you yourself included, so anybody, maybe if interested, you can pop the question. I think Dr. Parakram is here as well, so maybe he has something.
Yes, Welikala, it's nice to see you, and I'm really sorry I got a little delayed in joining the presentation, but really happy that you are taken the time to give a talk, and a very interesting one too. So just for the benefit of the students, can you just like very briefly tell how did you bridge the gap between the undergraduate studies and the postgraduate studies, especially going into a heavily mathematically biased area, and from there, how do you work your way through in learning new stuff, and what are the basically your life story during your postgraduate studies, and how does that relate to the undergraduate courses that you have taken, projects you have done, and things like that?
Oh, that's really good question. Thanks for asking that. And I must say, regarding the transition from the undergraduate, I was in faculty for I think almost 2 years when I joined when I came into BU. So I really
before you proceed, that's also another point I think you can highlight, because so in one might think that you had spent 2 years, so it was kind of like a delay, but eventually it seems like
it's really
not so you can
you made up for it, kind of a thing, no?
Yes, exactly. So I was really concerned. I think about I think you must have remembered that I tried to apply in soon after graduation and as well, but I think it's exactly correct. I was able to made up for that, and it really helped, because when I joined BU, and in the first year I had to usually in any PhD, the first year, the second year as well, is about the courses, taking the courses and spending time on the courses and finding a supervisor. So in my case, what happened was I found the courses to be really easy, not easy, but doable compared to the courses that I have done in the undergraduate at Peradeniya.
I specifically remember this point, right? Because I met you in Boston.
I remember.
I remember me and my brother were both like very amused by the fact that you just stayed at this particular theme park. And when we asked about the courses, he just said, "Sir, Harima lazy." So I remember.
So the thing is, this is about all the courses were about maths. So it's since systems engineering is about the maths courses, the linear systems, the probability, and the nonlinear systems, optimization. Since all of them maths, I think I was pretty comfortable with them. And I think as undergraduate students in University of Peradeniya electrical engineering course, I think the students will also feel comfortable. But I must say, having spent 2 years doing research and various projects, and I must say, while doing research at Peradeniya, I also looked up courses, and I had followed courses. So I was pretty comfortable when I joined the BU, and I straight away. So the first year I did research with my supervisor. So we have publications from that. So that's one reason that I was able to finish it within 3.5 years, because the first year I just from the first year I did research. It's like doing a PhD in some other countries.
So I think in an interest, I think Parakram, you brought up a very interesting point, right? That is, like, you make use of everything, right? Like, for example, for those who do not know, like Shirantha, I think your GPA was perfect or near perfect. I don't remember what was your.
Yeah, it was four,
right? It was perfect, right? And this was, you were the field top in a batch which probably had so many excellent students. I often say that, like, every single Parakram, I told Surimba, like, if you go for like Gayano, Chatumallo, anybody else, any one of them could have been a batch top in another batch, right?
Like, there were about 10 who could have individually be batched up in any other batch.
Any other batch, right? And so therefore, it was a very competitive batch, and you became the field top here, right? And on top, so that was all there. But still, like, rather than like just rapidly go to a PhD, you were here for about, I don't know, like 1 year and 8 months, or maybe 2 years even. I'm not.
Yeah, it's 2 years basically.
2 years,
if you round it up.
So,
yeah,
exactly. But then you were so mature, and you were able to quickly go into the research. You did the publications, and you finished off a US PhD in 3.5 years. And now you are starting on, like, sort of postdoctorate, or like, that kind of like post PhD research, right? So you managed to prove that point, that research maturity actually helps you to cover up for any lost time, right?
Any
so
loss of
that's
time.
clearly evident. Yeah. So in addition to that, like, is there any other, like, points that you, like, Welikala, would like to raise? And maybe, like, from the audience, maybe I see a lot of, not just the students, I noticed some of the instructors and RAs are here. Like, for example, Gihan, Harshane, Randi, Eranda, all these people are there. So maybe some of you all have questions, or maybe some of the final years or the EEES committee might have questions. So is there anybody who wants to clarify something?
Oh, I have a small thing. I think it's about the Dr. Parakram asked one question about the level of maths needed. So I think it's an important question to answer. It's not really complicated here. I think the undergraduate students at Peradeniya should do really well in any US program. But the thing is, you have to get the confidence. That only comes with spending some time doing research and working on some different problems. It's not about the math. The math won't be hard to handle. So the thing is the experience. Once you are experienced and confident enough, then you can. I'm pretty sure you can manage anything.
So in your, is there anybody else who has any? I mean, it could be of any form. The main purpose of this kind of thing is, as I think Praveen very clearly mentioned, it's about guiding your future. So whether you want to go for research, and the industry, but another thing that this kind of talk proves is that these things are not too far apart. Because we tend to think in Sri Lanka that, for example, when you go towards the research tracks and all of these things, that you get further and further away from the industry, which is actually not the case. So this is a very good place where you can actually, get a little bit more insight on to, you know, anything that you have, like, for example, you might have a specific plan, and you might want to inquire whether that plan is in line with this kind of, you know, pursuing higher studies. Will that help you? That kind of thing, right? Because I mean, as undergraduate students, you might not exactly know why you do a PhD, for example. You might just think that it is for one specific reason. So you might want to get a little bit of clarification there, and maybe even about the areas, right? For example, Shirantha, like you talked a lot about like systems engineering, right? So for example, you know, people might say, you know, they want to work in this field. So in that case, what would be a good PhD? And that kind of thing, right? So maybe some of these students have, right? Yeah.
Seems like Dr. Roshan.
Yeah.
Yeah, okay. Continue, sir.
No, you have a question?
Oh, no. No, I was going to ask from the participants whether they have questions.
Okay.
Participants,
Actually, I have. Is it okay if I present a question?
Sure. Go ahead.
Sure.
Yes, actually, you mentioned that first for the PhD you were following courses, and in the second year only you got to select a professor. So from what I have gathered, usually you write to the professor first and then look for the PhD course. So I would like to know how you managed to get into the course, what requirements were there when you entered into the PhD course?
Right, that's a good question, and a question that I had too while back. Right, so the first thing is I did write to professors asking about the positions and in USA. But the thing is, in USA, it's mostly it's good if you can convince a professor to get you as a student, but it's not very likely. So in US, you directly apply to the university, and then if you get selected, what happens is then you get to the university and do the courses. And while you are doing courses, then you get to then you can meet other professors there and then start working on their works. And if you didn't like some professor, then you can start working with another one in the following year or in the next semester, like that. So within first 1 or 2 years, you have to settle down with one professor. So that's the way that usually things go. But there are situations where you can contact a certain some professor, and if he is willing, then he will try to get your application through the university admissions, and then you will be able to join the university in that sense as well. But I haven't seen that happening in my batch when we came in. I didn't see that. Yeah, maybe I'm missing someone, but it's not common, right? So in the PhD, so as I've said, the usual way is to spend the first 1.5 to 2 years finding out a professor. So in my case, what happened was I got the acceptance from PU. Then since as soon as I got the acceptance, I got a email from the professor that that I worked with in my PhD. So it was like the other way around. So I got the email from the professor saying that I saw your application was accepted, and he told me about the research work that he's doing, and straight away I saw the connection with the stuff that I did in undergrads and the stuff that he's doing and his interests, and so. So I started working with him as soon as I joined BU, started my undergrad studies. So within the first years, first 1.5 years, he didn't expect me to do anything. But since the course load was kind of manageable, I was still able to do a lot of stuff. So that really helped. So in my case, it's like that. So I didn't spend time trying to find out a professor. I already got that resolved when I came in. So that was again a benefit. And I might add, it's again because of I spent a lot of time when I came in, as mentioned before, I had a certain number of publications, so that really helped as well. Yeah.
Thank you very much.
Are there any questions?
Yes, Velikala, a very general question. So how do you, since you have newly graduated, so how do you compare the life in USA compared to Sri Lanka during the course? But of course, you down with the entire world is down with the pandemic, but things are, because of that, things are different. But generally, from the field, what do you think of the general flow of life? And can you tell a little bit about that also, just as a
I think this is
graduate student's perspective.
Yeah, so since I'm in Boston, I think it's really nice place to be. And the fact that we have a lot of other universities nearby is really a good thing in terms of academic sense, because we often get a lot of professors coming in and doing guest lectures. So that's in terms of academic, but in terms of life, I think this is in USA. It's a nice place to be, and quiet, and you can really focus on the studies, and in that sense it's good. And there are a lot of other activities that you could do if you are interested in, like skiing and like the University Explorers Club that we have in the University of Peratini. There are clubs like that here. So there are a lot of activities going on those kind of groups as well. It's overall experience, not just academic sense.
Are there any other questions from the participants?
I think that's probably it, right?
Yes.
Is there anybody else?
Seems like me.
Yeah. So I think maybe we'll hand over to Dilhara and Praveen to conclude on it. But before we wrap up, again, Shirantha, I want to specifically thank you for sort of supporting this activity. And I hope to hear from you soon with many updates on your progress and such as well. Best of luck with all the activities.
Thank you, sir. Thank you very much, sir.
It was an interesting session. Now, to deliver the vote of thanks, I'd like to invite the Secretary of Electrical and Electronic Engineering Society, Mr. Sandulu Andasuri. Over to you, Sandulu.
Good evening. On behalf of all the participants, I would like to thank Dr. Shirantha Welikala for delivering such a valuable session. At first glance, it was a bit a complex topic, but with your explanation, you show us how our undergraduate knowledge relate to the topic that you covered. It was quite motivating as well. Thank you again for taking your time to deliver this session. Next, I would like to thank Dr. Prashant Godliadze for advising and motivating us to organize these kind of event as well. And next, I would like to thank Dr. Parakrama as well for participating. And then I would like to thank all the committee members of EEES for helping us in organizing this event. And last but not least, thank you for all the participants who participate. I hope you all get maximum out of this session. Hope to see you in next session.